So far in the class, we have talked about how to use Gaussian statistics and the Gaussian distribution to quantify the uncertainty associated with measurements that we're doing. And we're taking multiple measurements, and therefore we're dealing with the precision component and not the bias component of our uncertainty that goes into any measurement. And so we've talked about this rule of 30 samples being a large enough sample set for us to be able to quantify the uncertainty. But what happens when we have less than 30 samples? So maybe there's a situation in which we don't have enough money or resources available to capture more data, or maybe we don't have enough data available to us, even though it's a continuous situation where there's an analog signal or something that's happening in nature that's continuous, but we don't have enough resources to collect more than 30 samples or a minimum of 30 samples. So we are going to talk through students' T distribution. Section 3.6.3 in the book is a good section that talks about students' T distribution. And before we get into that, though, I'd like to just kind of reiterate, why do we even perform an uncertainty analysis? A good question for engineers is to always ask, why are we doing this? Is there value in this? Typically, our time is quite valuable, and so we want to make sure that we're utilizing that time in the best way possible. So I guess a few of them would be like standard practice for the industry, and so that helps us with litigation concerns. And so if we have a way of actually quantifying our uncertainty rather than just guessing or throwing out a number, that helps us a little bit with protection from liability. It also gives us a good sense of how good the data are based on the assumptions that are going in. Maybe they're historical or externally definable or verifiable. So it gives us a good sense of how good the data are. It also helps us understand the relationship between each source of error, so that when we're setting up our experiment, we can spend money in the right places and we can optimize or at least try to minimize the amount of error associated with our experimental setup. And then last here would be which component should we prioritize for upgrade or replacement? I mean, if we know which one is going to be the greatest source of uncertainty, then why not put that on our list of upgrades? So again, zooming out, thinking about a holistic approach or a mindset around this entire class, there's some key takeaways that we've got. All measurements include some sort of error, whether it's perceived or reality. They include some sort of error. And this is really important for we engineers to understand, because we are the ones who are doing these measurements. And so if we just take the word of our calipers or our any type of measurement device or thermocouples, and we just say this is for sure the exact right answer, I mean, we're being a little naive there. There is going to be a certain amount of error associated with every measurement. The second one, independent and uncorrelated. That's really important for us. If we're going to be using statistical means, we need to make sure that we have independent and uncorrelated error that are random for each measurement that we're taking. Bias can be handled not using statistical means, but rather doing a calibration or something like that, or maybe post-processing, where we subtract off a known value or a known trend that is moving the data away from the true value or the mean. Proper performance property or performance values that we get from tables or manufacturers. So as a design engineer, we're going to be pulling a lot of information from the table. So it's really important for us to know, where did these come from? What are the actual ranges? What is the uncertainty associated with it? And it's also very important for us to know if the manufacturer who's producing the product or material that we're selecting as an engineer, it's important for us to know that that manufacturer has actually followed a standard. So ASME, ASTM, there's some others out there who do generate standards that specify how they should be doing these tests. And so if they are done to these standards, now we can have a higher degree of confidence that the values that we are counting on in our design are the true value. And if not, what is the uncertainty associated with those values? We already talked about this, but the bias can usually be accounted for or corrected by calibration or some sort of adjustment of data afterward. Now, if we're to zoom out, again, high level from the class, these, in my opinion, are the 4 most important things that you can get out of this class. Number 1 is, how accurate do I need to be? We should always be asking that question before we take any measurement, even if it's a simple measurement. How accurate does this need to be? And do I have the right equipment? How accurate can I be with this equipment that's available to me, or how accurate can I be with the equipment that I've selected? And so doing a single point uncertainty analysis before we even take any measurements, even if it is a simple single point uncertainty analysis that we do in our head, it's very important for us to always ask that. How accurate can I be? And then how confident am I in the result? This is where the uncertainty comes in. We need to quantify that, because we can't just take it at face value. We can't be producing results and publishing those results to the public if we don't even know what our confidence is. If we're just blindly putting a number out there, that's not good. We are the technical experts of the world, and so we need to be able to quantify how confident we are in that result, which comes down to our uncertainty analysis. And then the last one is the most important topic that we can cover in any class related to mechanical and aerospace engineering, and that is, what are the data telling you? What is your interpretation of the data? If we just need a bunch of numbers crunched, we've got computers for that. But the interpretation of what the data are telling you, what decisions need to be made based on the results of the analysis, that is why we have highly trained engineers. Okay, so going back down into the weeds here a little bit of students' T distribution. We've got a problem here to solve to get our mind kind of around what we're going to be talking through. So as a new engineer, you've been tasked to record measurements from a diagnostic tool on a satellite repair robot. The robot is measuring electrical resistance of a circuit board using an onboard ohm meter. So obviously this is in space. Due to the other critical missions being worked on, you have been limited to collecting data for a duration of a 2-hour window. So you've basically rented this console that is communicating with your satellite robot repair station out in outer space, and you've been allocated 2 hours to collect your data. But unfortunately, the sample rate is 0.125 samples per minute. So we have a very limited amount of time. And you can see, based on the time and the sample rate, if we do some math there, we're not going to get 30 samples. We're going to get less than 30 samples. So what does that mean for our analysis? Our error associated with having less than 30 samples is going to be so great that we cannot use just standard Gaussian statistics to quantify our uncertainty here. And the last point is, the report must include your confidence interval, because we cannot include anything related to our uncertainty analysis without including our confidence, because as we've seen to great extent in class, that if we change that confidence, we are changing the bounds of our uncertainty by an exact relationship there. So what do we do if we have less than that? If we have small samples, we talked about this, where if we have less than 30 samples, we start getting some pretty huge errors associated with having a small sample set. And so we've also talked about how right around 30 samples is when we start having an error less than around 2%, if we make some assumptions in here and simplify this equation down for the deviations, and we look at it and we get down to around 2%. So that's kind of where that rule of thumb may come from, of 30 samples makes a large data set. So what do we do if we have less than 30 samples, like in our example that we've talked about here? Well, this person here, William Seeley Gossett, in 1908 was working for Guinness Beer, and he was one of their scientists or engineers that was working on the production of beer. And he found a way to correlate or maybe correct the Gaussian curve for samples less than 30. And so this was a huge finding because now he could take less samples and he could still reliably have a high degree of confidence in his result. And so the reason he published the paper under student is because he likely, I don't know this for certain, but he likely had a non-compete agreement and a non-disclosure agreement. But being a scientist, he did want to publish his results. And so his employer didn't want the competition to have access to their information, which is totally understandable. And so rather than have him publish it where someone may know that he works for Guinness and therefore they would be able to have access to some of their proprietary information, he was able to publish it under a pseudonym. So then no one knew who he was or who he worked for. And so it went out into the public domain. So it was able to help out all kinds of industries, not just the beer industry. And he published it under the pseudonym Student. And so it's a pretty interesting story there. Okay, so this right here, this T, certainly looks like our Z-score that we have dealt with before. It looks very similar, and that is because it is very similar. We have all of the same techniques that we use, but we have a new table. And so there's a couple of new variables, and that's really the only difference here is the couple of new variables. And so just like the Z that we had before, it is the number of standard deviations based on our confidence interval that we set. And so if we set a 95% confidence, then we are going to move our T relative to that, which is going to give us the area under the curve in that specific range. So the couple of new variables that we have here is degrees of freedom is the first one that I wanted to introduce, this new. And the degrees of freedom is like we've talked about before. If we start removing some of those independencies, we remove a degree of freedom. And so it's kind of similar. We are now taking that we're now adding in another dependency by having a different distribution. And this distribution, if you think of it, and this may not be exactly correct, but if you think of it as the correction factor or maybe a map between these highly inaccurate data points that are less than 30 to the Gaussian curve. And so we have almost a map, and that's what student T gave us, is this map that makes it so we no longer have that inaccuracy on the low end of sample number. So it's very similar to what we have in the Gaussian distribution. So we have these number of degrees of freedom, and that is number of samples minus 1. It's that simple. And so if we look at it, if we have if our degrees of freedom approaches infinity, we get right to a Gaussian distribution. Whereas if we start getting lower and lower, we can see that we have a different distribution. The probability distribution function starts to flatten out and get shorter and widen out a little bit. And so that's what student's T distribution is kind of that correlation between this distribution and the Gaussian distribution. And so we have a correlation between there. And so essentially we are getting the area under the curve for this new probability distribution function. And so T in this case replaces our Z in all of our probability calculations. So if we're interested in the true value or the sample mean of the uncertainty, then this is exactly like what we have going on with the Z-score. Now you notice that we have under here this sample standard deviation divided by the square root number of samples. Why do we have this in here? Because we are utilizing that central limit theorem. And that central limit theorem allows us to have the sample represent the population. And it also makes it so a distribution that is not Gaussian can be represented by a Gaussian distribution as long as we take a larger number of samples. The larger the sample size and the more samples we take, the more and more it represents a Gaussian distribution, even though the original distribution is not Gaussian. So if we're interested in the sample distribution, here is what we have, where X is the point of interest. So this equation is not in the book. This is essentially the z-score equation that we've looked at before, and we've replaced the z with the t. So here's our confidence interval. So this is what we're most interested in this class, is what is the mean value plus and minus some uncertainty. So our uncertainty here, again, is our z-score. In this case, we're using student's t, so it's the t-score, which is the number of standard deviations away from the mean, and our standard deviation. And since we're using the central limit theorem, we have s sub x over square root of n. And that tells us how far away from the true value we are, or the mean value of the population. So you'll notice that we have another variable in here, and that's this alpha. So if you remember, we had confidence divided by 2 in our z-score, and so this alpha is a little bit different, but it's the same exact concept. It's the area under the curve. And so instead of the confidence, we have the significance. So that's level of significance is our alpha here. So our alpha divided by 2 is what's replacing our confidence divided by 2. And so because we have this divided by 2, that it instantly makes us think, well, we probably have a table that is a one-sided table. So the relationship between our confidence and our significance is our significance is equal to our 1 minus confidence. So essentially what that's telling us is we're flipping over to the other side of that bound that we're setting on the distribution, and we're looking at the area under the curve on the other side of the bound. So what that looks like in this image is confidence interval. Typically we're looking at it under here. So this is 1 minus alpha, which is our confidence. You can see this equation right here. And so our significance is actually the tail side of this. So just like we had before, area under the curve, but it's on the other side of this bound that we're setting based on our confidence. So this is the table. So you can see here, we're looking up the value that's in this shaded area, which is our significance. And so our significance is going to be our 1 minus our confidence. So you can see that's what these values right here are, is our confidence minus, or sorry, 1 minus our confidence gives us these values here. And then our nu is our degrees of freedom, which is number of samples minus 1. So if we have 11 samples, we subtract 1 off of that, we're here at 10, and so we can look up our value. This is number of standard deviations away from the mean. So comparison, we've got our z-score here, and we've got the second, or sorry, it would be the second digit of our z-score across the top, and this is the area under the curve. So same thing, but we have our nu, which is degrees of freedom, and we have our significance across the top, and so we can pick out those same values. So hopefully you see that comparison between the two. We'll work through this example problem here in just a second in a different video, but hopefully that gives you a pretty good idea of the concept of student's T. So if we cannot afford to do 30 samples or more, typically we want to do everything we can to get greater than 30 samples, because there are always some inaccuracies associated with having the least number of samples. We've seen that before. We've talked about it in class. It's always better to have more than 30 samples, but if for some reason we cannot get at least 30 samples, then we have this correlation table that connects the Gaussian distribution to this new distribution of students T, and that's what this table right here represents, is that mapping.